Right, morning, afternoon, everyone. So this talk is about getting at debug and serial ports inside bits of hardware that you might have laying around, and it is, I suppose, aimed at those of you that are not necessarily hardware types. So if you're a software developer or a pen tester that doesn't really crack open bits of hardware to play with them, this talk is aimed exactly at you. A bit about me. I was in the IBM pen testing team for a while, left to run my own business. Really interested in SATCOMs and generally anything that's got a CPU in it and a clock. Love hardware and breaking it and tinkering with it. And I really like finding embedded TTY and serial ports in bits of hardware. I've got a Twitter page as well for nerd-related stuff. So, embedded serial ports. Not going to read everything on these slides. You can read them, but we'll talk a little bit about why you might be interested in a serial port. If you find a thing, it could be a VSAT terminal, a wireless access point from a manufacturer that doesn't want you to have access to command line, or another thing which is connected to a network. Often the Ethernet interface or the Wi-Fi interface is well protected, so it's firewalled, you can't get to the SSH service, etc. And for us, that's really annoying. We want a root shell on a particular thing. So embedded serial ports offer that possibility. Bypass the need to type in the username and password, boot the device, connect to the particular port, and you are automatically root in 99% of cases. Typically, the electrical interface is very simple. 3 wires are needed: ground, TX, and RX. Picture shows a typical embedded device with a debug header where I happen to find a serial port. You have to open the thing. You have to have the thing powered up while it is open. There is obviously a small risk that you could die if you touch the wrong thing. But it's not really anything to be afraid of. It generally only happens once. Delicate electronics can be broken. Here, a probe short resulted in a crater in the top of an IC, which is not the best because it generally breaks devices. Right, history of the RS-232 and the serial port. So the serial port is literally as old as dirt. It was designed a long time ago in the 60s. The original, these terms probably not too familiar nowadays, but data terminal equipment was mechanical teleprinters like the old Creed things, and data connecting equipment was modems, so point-to-point ISDN or bog standard modems. Lots of revisions of RS-232, but the one that is mostly used is RS-232C, and that is 0 volts and 5 volts to represent the 1 and 0 level. Typical baud rates back in the day were up to a whopping 1200 bits per second. Nowadays, every PC is, those PCs, I should say, that do have proper serial ports on them, is compatible with RS-232C, so that's 0 and 5 volts. You can interface a lot of stuff to that. Lots of connections. Original RS-232 ports, 25 and 9-way. On the 9-way, pin 5, 2 and 3 were used. On the 25-way, pin 2 and 3 were used for TX and RX, and there's numerous grounds. But you don't really see this stuff on computers nowadays because we've gone to this universal serial bus stuff. Typical RS-232 signaling format. So whenever you see serial data discussed and you see a number characters like that, 7E2, that is describing the protocol on the wire. 7 bits of data, even parity, 2 stop bits, and you can see in the diagram. A10-1, which is pretty much what most embedded devices are, 8 data bits, no parity, 1 stop bit. LSB is transmitted first down the wire. Odd parity, a little bit about parity. The parity is there to determine whether or not there is an error in the data that is transmitted. Bear in mind, when RS-232 first was around, people would have miles of cable with a 1200 baud signal going down it, and electrical interference could cause data to be corrupted. So the solution was parity. If a byte was received with an odd number of ones, but the parity bit said that it was even, then you know that the bit is in error. most things nowadays have no parity because error correction over a foot of cable is not really too much of a problem. So a couple of hardware implementations. We just talk about things that were in my junk box. So when you pick a piece of hardware apart, the first thing you should always do is take the lid off it and work out what is going on inside. There's two ways you can do it. You can look at all the chips under a microscope and then Google for the data sheets. I would highly recommend that. Or you can just guess what the parts do by where they are on the board. And that's actually a valid technique. You can see, for example, the Toshiba is probably a RAM chip just by the form factor and where it's on the board. The Samsung chip is near the HDMI interface, and that is probably a graphics processor. And then the Broadcom is probably the CPU, and that's probably power management, something like that. In fact, it's an audio DAC. But you can read the data sheets, but the most important thing to do is to look at the CPU, in this case the Broadcom, get the data sheet and look for particularly interesting functions in that device. Here is a couple of excerpts from the data sheet. These things are several hundred pages long, but read them, and the bits that you're really interested in is where it says 2 high-speed UARTs. So a UART, Universal Asynchronous Receiver Transmitter, is a serial interface embedded in the micro, and usually these are used for one thing, and that is debug ports. So, looking at your PCB, you can see test interfaces. They're highlighted in the yellow boxes. Test interface next to the HDMI processor may not necessarily have serial. A test interface somewhere near the main CPU probably has a UART on it. Test interface down here near static RAM or the HDMI processor is probably another test interface specific to that processor. Not quite enough pins for JTAG, but there are methods that you can use easily to determine whether or not a port has synchronous and async data on it. Before we look at that, we have to discuss the delicate topic of magic smoke. This is basically stuff that comes out of electronics when you do bad things to it. And believe it or not, you can actually you can either smell the smoke or look at the colour, and that generally tells you how bad the fault has become, or if something is on fire. I did find this on Amazon, which I thought was quite interesting. It's RoHS compliant, and it's a magic smoke refill kit. So if you do end up with a crater in the processor, you can buy this and it will fix it. So it's always worth having in your junk box. So most devices, this is the device which is the victim of the hack later. It's a wireless access point from Cisco. There is nothing wrong with prodding around in this device when it is connected up. You won't hurt yourself or get burnt or catch fire or die because it only runs from 12 volts. The difference, if you're looking at a device that has a mains power supply built into it, then you have to be really careful. Obviously, if you touch heat sinks in the switch mode power supply, you will be woken up quickly, and you will probably won't do it again. So you just have to bear in mind what it's powered from. If the device uses a wall-wart type power supply, you are fairly safe, unless it's a really cheap Chinese power supply, in which case the negative rail is probably floating at half mains voltage, so 110 volts. Check with a meter, so put it between the ground, any metalwork on the thing that you're about to look at, and a ground socket, poke it into the ground pin on the main socket, and just measure. Sometimes it will show 120 volt AC. It will be a very low current. You could probably feel it if you put your fingers between the two, but what you don't want to do is put a PC interface between them, because magic smoke will come out of the PC. You will be annoyed. If in doubt, get a DVM, digivolt meter, and measure, put it in AC, and measure the voltage. And the most important bit about fiddling with hardware, don't let your own magic smoke release, because there's no real way back from that. So tricks for locating serial ports. There's a few ways you can do it. You can get a scope and prod around on pins and look at the waveform for something which looks like a classic asynchronous signal. So a start bit, 8 data bits, and a stop bit. I like the audio amplifier and scope probe method. So you can build this with minimum cost and components. Use a 99p sound card which has a mic input to your PC. If it goes pop while you're connecting mains to one side, who cares? It costs 99p. But you can listen to the data, and with practice, you can say, oh yeah, that's 57.6, 7E1, or that's 115.200, 8M1, and you can estimate the baud rate, but you do need to practice that. You can buy a TTL to USB bridge, such as a small, a few pounds interface, which has 5-volt logic in on one side, USB output, and will be seen, for example, like /dev/t2i USB 0, and then you can iterate through baud rates, parity, number of stop bits, number of data bits. That is a little bit annoying. You can use a logic analyzer to measure the bit length. Once you've got the length of one bit, you can work out how long it takes how long that bit takes to transmit. Very simple sum to work out the number of bits per second, and therefore the bit rate and the speed of the data. Listen for asynchronous data bursts. So I don't know whether this will work if I tap it. No, it won't work. But I'll play you the audio in a minute, just so you can hear what it sounds like. Lots of things, when they boot up, particularly with Linux kernels, you get lots of dots saying loading Linux kernel. And that is something that really sticks out when you use the audio port method, because as the thing is booting up, you can hear tick, 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 followed by a burst of noise when the kernel loads and starts to do stuff. Once you have found a particular pin, this is an example of a really cheap TTL to USB interface. You, to start with, only need two connections, the ground connection and the data input connection to here. So you connect it to the RxD pin, and then use something like Minicom to estimate the baud rate or type the baud rate in, and look at the data to see if you've guessed correctly. Typically, if you guess a baud rate incorrectly, you'll get garbage like this. So if the baud rate is low, 1200, 2400, something like that, and you've typed in 115.200, every bit that comes out of the thing, the PC is going to try to interpret that as a single bit, but in fact it's dozens of bits at the high speed. When you eventually find the correct speed, usually you get ASCII printable text out the backside of it. You do occasionally find manufacturers that have thought about the embedded UART attack, and so at a point in the kernel they will remove the module so you can't actually do anything. But the number of manufacturers that do that, you can probably count on one hand. A logic analyzer. So IKA Logic, this is again a cheap and cheerful logic analyzer. You can connect the pins up to ports that you think are TTY or an internal UART, and do basic measurement of them to work out bit length and see whether the data is something recognisable. The IKA Logic Analyzer, which is one of the ones I have, has an ASCII decode in it, and you can see here it says booting space, and it would say kernel, etc., and then the thing would load. But this is typically what you would expect to see on the output of a logic analyzer, and you can see the gaps between each character, which is the stop bit. So a demo. This is not a live demo. I have done live demos before, but they live demos. So this is the thing. This is a Cisco Meraki access point. I'm sure some of you are familiar with these. They're an access point which you really have no control over, apart from if you pay Cisco money to access the portal to manage these. The actual device has a VPN endpoint in it. It chats over internet, connects to Cisco. Their portal pushes config data to your access point. There is an embedded UART in this device. So you can see on the picture areas where you might start investigating. So lots of pins. You can see the RAM, the power management stuff for power over Ethernet, and the main bug, and then the main CPU, and then under here are the Wi-Fi transceivers. So for me, the main area to start would be pins nearest the micro. So here is the main micro. There was 4 blank pins here, which I fitted headers to so you could get a scope probe round it. So when listening to these pins, you could hear something which sounded very characteristically like 115.200 AM1 serial data. And of course, the next step is to connect that to Minicom and see whether or not you can find something. What I've got here is just a quick photo of it on the bench. So there's a scope probe connected to a scope, so I can see the waveform, and the red wire is a single wire that's connected to the RxD input of a serial UART. Right, I just need to escape out of PowerPoint and go to the video. There we go. So here, this is Minicom under Linux. So you can hear some noise, and that noise was an audio tap from the pin. And this is the Meraki Kernel Booting doing its SHA-1 hash check. I don't have a whole video where it comes to a hash prompt with root, but you get the idea. If you were to wait a few minutes, you would see this scrolling up with, as we know, bog standard kernel boot. In this particular case, they have a protection mechanism in to stop people playing with TTY console, and that is a warning which says don't play with this via the serial console. Really? Yeah. Hold on, let me just get back. Needless to say, somebody who was of a nefarious character might log into that, or might connect to that terminal and realise that there is a VPN interface with an address assigned, and perhaps explore that, etc. But there's, I would say, lots of devices have these internal debug ports. You can do a lot of cool stuff with it. VSATs, so a VSAT modem is a modem which connects to a satellite antenna. They're one of my favourite things to play with, especially things like National Lottery terminals, because they are really they are well secured, and from the Ethernet interface you can't actually do much. However, there's an internal UART interface that gives you a VxWorks root user, and of course from there you can delete the firewall, you can do all the things that you need to do to then be able to get a web interface over HTTP, etc. So that is a whistle-stop tour. It is very easy to do. I would encourage you to, when you get home, to look at in your junk box for stuff that's got an Ethernet interface, get your screwdriver out, take the lid off, have a look at the board and just probe around, make a very simple interface, literally a bit of wire that connects to a mic input on a cheap USB sound card, and just have a play with this stuff. Start with things that are powered via wall warts, so plug-in power supplies in the wall, because you've got less chance of killing yourself through contact with mains, but just play with the stuff and see what you can find. If you've got managed switches or routers or stuff like that are chucked in junk box, get the lid open, have a look at it, Google the part numbers, find the async ports, and get on there as a root user and see what you can do. But you can have a lot of fun with this, and it does save an awful lot of time. On a router, can you find a command execution through an input field on a config form that they haven't properly bangs checked? You can save all that hassle by using the internal debug port. That is it. So a really quick talk. I will have the stuff out on the table with the access point and the audio stuff and the TTY interface, so you can see this and play around with it and hopefully not blow yourselves up or my board. Is there any questions?
Question here. So in the first picture you showed, first, you had a resistor soldered to one of the right pins, I think. I've seen that before, but I haven't actually seen any explanation of why it's necessary.
So I picked a 1K resistor because it just happened to be on the bench, and all it is for current limiting. So sometimes if you pull down a particular port, you might find that bug moans about that and it won't boot properly. So the current requirement for a USB to TTL is, microamps really, and you put a current limiting resistor in series to prevent you loading the pin down. The other thing is if you accidentally touch a 12-volt pin, Magic's Mate won't escape from anything because you've got a current limiting resistor. So that's all it's for, just a bit of protection. It's laziness on my part because I didn't measure it with the scope first. But anyway.
I would also say that listening to raw serial is a path to the dark side. How long did it take you? I mean, I appreciate there's a finite number of options in parity and speed, but how long did it take you to figure it, like to be able to guess what configuration it was by audio?
So stuff above 115-200 I struggle with because at that point it's just bursts of noise. But, the low speed stuff is quite simple. 1575 board by ear is a little bit difficult to tell the difference, but it takes 20 years.
If you listen to it backwards, is there any specific messages you get from them?
We can't talk about that in public.
You set it as your ringtone?
My current ringtone is a modem negotiation, but I could have,
How resilient is the interface? If you start trying to force the interface, for example, how likely are you to crash versus cause
unexpected things happen?
Unexpected non-deterministic effects.
Yeah. So the majority of debug interfaces in embedded stuff, for example, the Meraki AP, it is the same as being able to SSH or telnet into it. So the answer is the same as what would happen if you were to send characters over telnet or SSH. But the attraction is when you instead of SSHing or telnetting where you've got stuff in the way, so IP tables or something else that would prevent you accessing the service behind it, with the serial port, the embedded UART, you're talking directly to the end service, so the kernel or whatever it happens to be, at hardware level. But fuzzing, I don't know. You would break it as you would break it over telnet or SSH. Any other questions?
So I had a quick one.
Yep.
I wondered if there was like an entry level logic analyzer you'd recommend. Like I saw some discussion. I just had a quick look when you mentioned it. I couldn't see it on Amazon or eBay. And I've seen talk about $10 sailing clones and whether they're any good. And I saw something recently about there's a patch for the kernel for the Pico that you can use that as an analyzer. But
yeah, so you can use Raspberry Pi. There's GPIO pins that you can read quickly, and that will do exactly the same as the logic analyzer. But this thing is cheap, so if you accidentally connect one pin to mains and it goes pop, fine. Do you want to destroy a Pi? I mean, I know they're only tuppence, but
not at the moment.
Oh no, not at the moment. Of course, you can't get them anymore, can you? But no, the ICA logic analyzer, I think they only sell it on their website. But you can probably go to AliExpress and find a copy. But it might have a free gift inside if you Oh, that's it.
Is there a way we can is there any good books or projects that you recommend or resources online to get familiar with this level of hardware interaction? I can barely solder a radio together.
That's fine. Yeah, you only need soldering skills to fix it once you've broken something. But the main thing to do is find cheap or free hardware. Ideally, you want something low voltage that has Ethernet and a bug in it, a micro in it of some sort, and take them apart and just learn by doing. If half of them you destroy, it doesn't matter because it's free stuff, but I would pick old wireless access points, old routers, anything that that has a UI and you get the impression that there's a kernel of some sort running in it. Take the lid off, Google the part numbers, look through the data sheets, but learn by doing. And you can spend weeks reading a book, or you can spend a weekend messing around with the stuff and honing your skills. But Google, I suppose, is the answer. Hardware hacking, yeah.
How often are the actual super 95% control process in this code? How often was that some hash
So VX works you see quite often in phones. I've had a VSAT modem with VX in it, which was painful because they've done a really good job bolting it down. But I mean, it's nothing that can be undone. It just took longer than it would have done if it was Linux. You get the odd thing, I can't remember the name of the product, but it's a thing that controls lights in corporates. And these things are PIC processor, and it's an operating system they've written, and you can't really do much of it. I mean, it was designed to do, turn a light on and off and make it flash different colours, and there's not really anything you can do under the covers. And plus it's a PIC, you can't even read the code out because they've protected it. But it's rare. Most stuff has been put together with a bug that supports Linux, and of course they just chuck a kernel on and write some shoddy code and leave the UI exposed. So I would say most stuff is Linux.